Okay, so I hope I'm audible. Now, let us start with TCP/IP questions. Okay, so I hope you have already seen the videos that I have uploaded. Now we will be just starting directly with the questions, or maybe I can just recap you few of the things. So let me just quickly recap you that what we have seen in the TCP/IP videos. So yeah, so let me start with the TCP. So today we will be just seeing TCP and most of the things about the TCP, and then in the next lecture we will be just finishing up things in the TCP, and then we will be just also doing the UDP protocol. So anyway, this TCP is the large portion of transport layer, and UDP is just a very small portion, because in UDP there is nothing much to study. Okay. So this is UDP, and then let's start with the TCP. So TCP is a byte-oriented protocol. It means that it actually counts every byte. Like whatever you are sending, it keep track of every byte. That's why it is called byte-oriented protocol. Also, it is a connection-oriented protocol, which means that you will be establishing a connection before you start the data transfer. It is also full duplex. Okay, so which means that even though there are a client and there is a server, and maybe let's suppose the client doesn't want to send any data, or the server, like generally server sends the data, but in that case also, like it's a full duplex. It just gives a facility for both of them to send the data and receive the data. Okay, so let's suppose this is a sending process. Since it's a transport layer protocol, so it is basically communicating between two processes. Let's suppose it is a sending process, it is a receiving process, and then it is a stream of bytes between these two processes, and that's what TCP handles. So it is a connection-oriented service, which means unlike UDP, it is a connection-oriented protocol. When a process at the site A wants to send and receive the data from the process at the site B, the three-phase occurs. So there's in the three phases, the connection happens, right? So that's what we will see. So like how does the numbering system happens, how the number behaves, and what is the acknowledgement number, and these we have already discussed. But let me just tell you very quickly. So suppose that you are sending some packet, and that packet you are having some bytes that is of byte number X to byte number X plus 499. Then the sequence number will be just X. Sequence number is the number of the first byte, right? And then let's suppose you're sending after that time you're sending X plus 500 and then X plus 500 plus something. Then the sequence number will be X plus 500. Why? Because this is the sequence number of the first byte. Okay. And what is acknowledgement number in case of TCP? So TCP acknowledgement is cumulative, which means that that if you are sending the acknowledgement number is X, it means that all bytes before the X has been received. Okay. So acknowledgement number defines the number of the next byte that party expect to receive. If you are sending X as an acknowledgement number, then what does this mean? It means that all before the X has been received. Okay. So suppose that if I'm saying if a party uses 5643 as an acknowledgement number, then what does this mean? Or does this mean that total bytes received? So if it is saying 5643, okay. So let me go here. Yeah. So if a party uses 5643 as an acknowledgement number, then what does it say? Let's just see this. See, if you are saying 5643 is your ACK number, since it is cumulative, it means that you are now expecting to receive, right? It means you are now expecting to receive 5643 byte, right? And what does it mean? It means that you have received all the bytes from the starting sequence number to 5642. Okay. Initial sequence, there is something called initial sequence number to 5642 you must have received. Right. So party has received all bytes from the beginning. Beginning means initial sequence number. Okay. Beginning doesn't mean the sequence number is 0. Beginning basically here it means that initial sequence number. Okay. So it has received from the initial sequence number to 5642. Why the random sequence number? Why not 0, 1, 2? Yeah, it is a good question. Like why we are choosing a random sequence number? Maybe because see, what happens that since the TCP is full duplex, if you're sending from like sequence number 0, you can do it. Like there is no provision that you should not do it. But if both are basically having sequence number 0, sequence number 0, right? I mean, both are doing the two-way communication. It is sending some data. It is also sending some data. In that packet, if let's suppose the sequence number 0 is the first sequence number, in this packet also, let's suppose sequence number 0 is the first sequence number, then probably there would be a confusion. I mean, whether, like, I mean, this is the data that you are expecting to receive, or you are sending, or something like this. I mean, you can do it. There is no provision. I don't think that there is no strict answer to it that why you don't want to do it. But maybe just to avoid the confusion, like, because it is a full duplex. So maybe this could be the answer, but I don't think there is any intuition even, or any heuristic that why we should not do it. I mean, we can do it, but maybe just to avoid some confusion, we may not want to do it because it is a full duplex. Okay. So I hope you got this question. Mean that if you are sending 5643, it means you have received everything starting from initial sequence number to 5642. Now, since it is a full duplex again, then there will be two windows. Generally, there is nothing sender, nothing receiver, because both sends and both receives. But let's suppose it is host A. Generally, let's suppose left hand side is sender. So at this side also there are two buffers. One is called sending window, and at this side also, I mean, only there are two buffers. One is called receiving window. Okay. Similarly, here also that's the same story. Here also you will be having the sending window and the receiving window. Which means if you are sending something, you will be sending from here. If you are receiving something, you will be receiving in this, right? So there are two buffers at every side. Now let's talk about the TCP flow control. That how does the TCP flow control happens? Okay, TCP uses selective repeat for flow control. And interestingly, like generally in the selective repeat that we have seen at the data link layer, in that case, ACK was selective, right? I mean, individual ACK was there, but here the ACK is cumulative. So that's the key difference between the selective repeat at data link layer and the selective repeat that it is using at the transport layer. So the ACKs are. So why we are saying it is selective repeat? Because at the receiving end also there is a window which is not just having one packet, it can hold multiple packets, right? So at the receiving end also, let's suppose it is a receiving window, there are, like, it can hold multiple packets. So there's a window, since it is holding multiple packets, that's why it is definitely not go back end, right? So that's why it is selective repeat. And then I'm using the cumulative ACK, that's why it is called selective repeat with cumulative ACK. Okay, so let's see maybe with the example. So here, like sending window is looking like this, that this is the first byte that for which you are expecting to receive the acknowledgement. And then once the acknowledgement is received for, let's suppose, this byte, I mean, generally that's for the one segment. Okay, so once the acknowledgement is received, then you will immediately slide your window, and then you will immediately send this byte, right? Just like a sliding window that we have seen earlier. So similarly, in the receiving case also, these bytes you have already received, and you have already maybe passed to the application layer. Okay, next byte to be pulled by the process. Maybe these bytes you have already received, and then you are expecting to receive this one. Okay, maybe 261 byte number, and then tell me, have you already received some byte in between also? Can you receive some byte in between also? Which means that if this is a receiving window, okay, so let me just tell you what do I mean. So let's talk about the receiving window. So let's suppose this is the total allocated buffer that you have. Okay, this is the total allocated buffer from here to here, which means that you can keep your data from here to here. This is called allocated buffer. Now, suppose that in this like in this buffer, you've already received these many bytes. Okay, you've already received these many bytes. If you have received these many bytes, then what you can do, you can pass those bytes to the application layer, right? Application process. So these are received. You can pass them ready to send to the application. But let's suppose the application that process is currently busy. It's not handling the data that fast. So you can just keep it with yourself. And these are the bytes. These are the bytes which are already sent, right? These are the bytes on the left hand side which you have already sent. So let me say these are the bytes which you have already sent. Received, obviously these are received, and sent to the process. Now this is the first byte that you are expecting to receive next, right? This is the first byte that we are expecting to receive. Okay, this is the first byte you are expecting to receive. Now tell me, can you receive in between any bytes? Like bytes means like it's a continuous byte, basically the segment size. So can you receive any in between segment size? Can you say that this is also received, this is not received, this is not received, but this received? Is this possible? Yes, this is very much possible, right? So this is very much possible because we are using the selective repeat. So that's why you will say, yes, this is possible, right? So maybe this is the first byte you are expecting to receive. This also you have received, but the moment you receive these many, okay, the moment you receive these many, then you will immediately slide your window. Okay, so whatever is your window size, you will immediately slide this window, right? I hope you understood. So see here, the same thing I have written here also, that in the screenshot. So basically this is the first byte that you have received, but you like, I mean, this is just in the buffer. Anyway, this is not of much interest. Let's just focus on the receiving window. So this is the first byte that you are expecting to receive. And the moment you receive this byte, you will immediately slide this window. Let's suppose that in between also you have received something. So the moment you receive the continuous bytes, you will immediately slide your window to the end of that contiguous bytes, right? Okay. Now let's look at the TCP header. So basically, now currently I'm just pausing my discussion on the flow control. So like I want to discuss the flow control, but before that, let's just discuss the TCP header, and then we will just see the how this flow control is happening using the selective repeat. Okay. So we will discuss the flow control, but just in a while. So I have just given you the idea about the windows, but after this header, we will just come back to the flow control. Okay. Great. So this is how the header looks like. There are different fields. Now, obviously, it is a port-to-port communication, very reliable communication. So you must be having the port addresses, the source port address, destination port address, and these things are there, right? So it must be there. Now, a sequence number, acknowledgement number, like these things are there. Now, just like the IP header, I used to have the header length, which is of 4 bits, which means that at max I can represent 15 here, right? I mean 0 to 15 I can represent. But the header length total could be 60. So just like a IP header, I also do the scaling from 5 to 15. I hope that is fine to everyone. Okay. So it is just like the IP header. Now, these sequence number, acknowledgement number are very interesting fields. I mean, the port numbers are just obvious that, okay, there will be port numbers. But the next fields which are interesting to us is sequence number and the acknowledgement number. And then the next interesting fields are these flags. So let's just look at these fields one by one. Okay. Sequence number, acknowledgement number, these flags, window size, urgent pointer, checksum, these things. Let's just look at one by one. So let's talk about the sequence number. So what is the sequence number? As we talked earlier, if it is a basically the sequence number of the first byte, right? If the first byte number is X, then the sequence number will be X. Then how the receiver will be calculating the last byte number? let's suppose that it has to send the ACK. Okay, it is based upon the, can anyone tell me? So basically the sequence number will tell you what is the first byte that you're receiving, right? And then you have to send, let's suppose, the ACK. Then obviously you have to check what is the last byte that you have received. So how you will get it? Yes. So basically here you do not have the total length field, but you can get the total length from the IP header. So we will see this. Okay. So, okay, let's just go one by one. But here you do not have the total length field. You will get the total length from the IP header. So sequence number, you got it right. I mean, it is the sequence number of the first byte. Acknowledgement number is something that you are expecting to receive next. Okay, expecting to receive from the other party. This is the acknowledgement number. Okay. So let's see these flags. There are 6 flags that we have: 1, 2, 3, 4, 5, 6. Now, generally, this URG and PSH flags are not being used. Okay, I mean, these are just for the theoretical purpose. I will tell you the use of this, but practically, this URG, in fact, no one have used it in any application. Okay, I mean, this URG and PSH, these flags are never used. But yeah, we will see the theoretical meaning of these all flags. And all other flags are very important apart from this URG and PSH, because no one uses this URG and PSH till now. Okay, no application has uses URG and PSH flag. So let's just see each flag one by one. So let me just first talk about these flags, which is SYN flag, FIN flag, and ACK flag. Okay, so maybe if you have seen the videos, then we can quickly go over the slides only. So first flag is, let's suppose, the SYN flag. SYN flag is one. It is for first what you do the TCP connection, right? So the first step is to do the TCP connection. Yeah, connection establishment. Now, as a sender, or let's suppose it wants to send some, it wants to get some data, then it will say that, okay, I want to establish some connection. Then to say that I want to establish some connection, it will say the SYN. SYN means that I want to establish some connection. Initially, this SYN equal to 1 means that, okay, I want to establish some connection, and then ACK will be 0. ACK means like I do not have any acknowledgement to send, but I want to establish some connection. Now, suppose this is the client, this is server. Okay. Now tell me, should let's suppose if I have two files, one is client.c, I mean just for the illustration purpose, and one is server.c. If I have two files, then should I be running this server.c first or the client.c first? Tell me. First, what should I be running? I will be running which one? Client or server? Server, right? Why? Because server should be on the passive open condition always. If server itself is closed, then there is no point in sending any request to the server. So server is always, I'm assuming, it is in the passive open condition. Passive open means it is ready to listen. If someone is sending some data, I'm ready to listen. Okay, passive open. I mean, I do not know whom to contact, but if someone is contacting me, I will reply. It's like that, right? I mean, server is like a helpful person. So if someone is going to him, then it will help him or her, right? But server doesn't know that whom to help until and unless someone asks, right? So it's in the passive open condition, or yeah, listen state, you can say, right? So now you send the first packet, which is called SYN packet, and you say that, okay, this is my SYN packet, and then server will say that, see, it means that you might want to establish a TCP connection with me. Then it is just like a normal packet. It's nothing new in this. Normal packet means what? Do you remember I talked about how all the layers work in that lecture, right? So the first packet that we send, okay, is the SYN packet, which means that first step is the DNS, right? After DNS, you just do the TCP connection. In that you send this SYN packet and all. And once the connection is established, let's suppose you are in the HTTP mode. I mean, this you're contacting to the web server. Then you do the HTTP transaction. Okay. So these are the set of steps. right? So basically this TCP connection is just this SYN packet is just like a normal packet, which means let's suppose that you are in just one network and this is one host here, and there is some another network in that there is one server, okay, and it wants to send a SYN packet to this server. Then it is just like a normal packet, which means it will first get the MAC address of this gateway using the ARP, and then it will send here, then like that, just like a normal packet that we talked about. So this SYN is nothing special packet, is just like a normal packet, okay? So it is sending a SYN packet. SYN equal to 1 means if all the flags are 0, if SYN is just 1, it means it is the first packet that someone is sending. Then I will say that okay, I'm also ready to accept your connection. I also want to establish the connection. Then SYN equal to 1, and then it will say that it will acknowledge this previous packet, right? So since it has to acknowledge the previous packet, that's why let's suppose the sequence number. There is some field called sequence number in the header. See here, the header is having some sequence number. So whatever is the sequence number that I have written there, I will say let's suppose the sequence number is X. Then I will say ACK is X plus 1, which means I have accepted this. Now I'm expecting to receive something else. Now it will say that okay, I have also received it, which means it will send the ACK, which is, let's suppose here the sequence number is Y. Then ACK will be Y plus 1. Is this okay to everyone? Now tell me, will the first packet will be carrying any data? Are you carrying any data in the first packet? No, it is just a connection establishment phase. Until and unless you establish a connection, how can you send any data, right? So since you are just establishing a connection, so you cannot send any data in any of this packet basically. I mean, you can send here at the last because the connection is established, but yeah, in these two packets at least you cannot send any data. So here there is no data sent. Still, you are basically having some sequence number. Okay, this is called the initial sequence number. See, you are not sending any data, still you are writing the sequence number. Why? Because you want that to be acknowledged. So once it is sending a X plus 1, then you will get to know, okay, my packet has been received, right? I hope you understood. So basically, you are choosing some random sequence number, and then once it says that okay, this is X plus 1, then you will get to know that okay, this packet has been received, and then it will also write some sequence number. Although it is not sending any data, still it will write some sequence number because it also wants to get acknowledged. So basically, it is again some random sequence number at a start, then it will acknowledge it, right? Now in this packet, you can send the data if you want. Okay, if you want, you can send the data at here. Data in with this basically. So this first packet does not have any data. Still, it consumes one sequence number, right? Similarly, this packet does not have any data. Still, it consumes one sequence number. Now tell me, is it consuming any sequence number? Suppose you are not sending any data here. Is it consuming any sequence number? No, right? It is not consuming any sequence number. So if you're not sending any data, then it will not consume any sequence number. Why? Because you don't want this to be acknowledged, right? It is just the acknowledgement that you are sending, and then there is no acknowledgement for this particular packet. So that's why there is no sequence number that it will consume. Okay, so it will not consume any sequence number. Yeah. So SYN is basically saying that your sequence number field is valid. Okay, if SYN is 1, then it means that sequence number field is valid. Now, in this case, SYN will be 0. SYN is 0, which means that your sequence number field is not valid, right? So SYN 1 means sequence number field is valid. Similarly, ACK 1 means ACK field is valid. Okay, your sequence number is valid. It means it is actually containing some sequence number. So initially it actually contains some sequence number. Next also it actually contains some sequence number. Tell me, does it contains any sequence number here in the last packet, then the third packet, in the connection disturbance? No, right? So that's why SYN is 0. I mean, you can send the data, but it is not necessary. And ACK equal to 1 means ACK is valid. I hope you have understood this. Let me know if there is any doubt. Okay. So ACK indicates the acknowledgement number field is significant. Similarly, SYN indicates the sequence synchronized sequence number. Only the first packet sent from the each end have this flag set. Only the first packet sent from the each end should have this. Okay. Just a second. So this is frozen. So see here about the SYN. Yeah, these are the control flags. Okay, so my only confusion is that this SYN is one for only the first packets, or it is one for the all the packets. That's what I'm just quickly looking for. Okay, it seems like SYN is one only for the first packet, right? Cool, no problem. So this SYN is one only for the first packet. So it is used to synchronize the sequence numbers. And if SYN is one, it means that it is a first packet from my side. Okay, synchronize only the first packet sent from each end should have this flag set. So it means that okay, SYN one means that it is the first packet from my side. Yeah. So SYN one means it is a first packet from my side, and then ACK one means that ACK field is significant. Okay. So now let's look at the other fields, which are the SYN and ACK is okay. Now let's look at this FIN. What does this FIN says? It is basically used for the connection termination. So I will talk about this FIN, but before that, maybe let's talk about this PSH, RST, and URG. So what is this PSH? PSH, if PSH is one, it means that it is telling two things. Okay. So if PSH is one, first is that at the sender side, okay, sender is doing the PSH one. At the sender side, application process tells TCP that you send this data immediately. Immediately means without waiting for other bytes to come. Although these flags are not being used in the practice, like if you look at the Crow's book, then it is clearly written there that these flags are not being used in the practice. PSH flag and URG flag are not being used in the practice. Okay, but anyway, just for the theoretical purpose, we can see this. So PSH is one means that that is at the sending side. Okay, so let's suppose this is a transport layer and the application layer processes the data, right? It keeps the data here. Let's suppose this is the buffer, sending buffer. Okay, now generally what happens that you wait for the enough buffer to fill and then only you send the data, right? But if the PSH is set to be one, then I will say that okay, don't wait it to be full. Maybe you just have this much data. Okay, in the buffer, you whatever data you have, you just send it immediately. It is just saying that don't wait for the buffer to get the sufficient full. Okay, PSH1 at the sender side means that just send it immediately. Don't push it to the network. Don't wait for me to fill the data. Something like this, right? And similarly at the receiver side, it means when the receiver receive it okay, at the receiver side, what does it mean? It means that application, whenever receiving the data, then it means that the transport layer should be pushing that to the application layer immediately. Does it mean that we are sending out of order? No, it just means that the transport layer at the receiving will not wait. Okay, transport layer at the receiving end will not wait for the other data to come and push to application, right? It means that we are not waiting at the receiver side also, we are not waiting at the sender side also not waiting. Okay, so let me tell you what does it mean. So suppose this is the sender, okay, and it is waiting for some data to come from the application layer. Now suppose the application layer is sending this much data only. Okay, this is application layer is providing you this much data. This is transport layer buffer. Okay, this is buffer, or maybe you can say sending window or something like this, right? Let's just call it sending window. This is the sending window, I mean a window at the sender side. Now, generally what we do, we basically say that, okay, let's just wait for the other segments also to come, and then we will send all the segments together. But if the PSH is set to be one, PSH is one, then it will not wait for the other segment. It will directly push that to the network, right? It will directly send it. Now, when the receiving end is getting that data, okay, if the receiving end is receiving this data, this is the receiving window. In that case, what will happen? If the receiving window is getting this data, it will not wait for this to get full, obviously, otherwise there will be no purpose of PSH, right? It will also not wait for this to get full. It will immediately push to application layer. That's all. I mean, if this much data only, then it will immediately hand over to the application layer. That's what the push means. Does it mean that we are handing over out of order data, which means if let's suppose there is still some data to be pushed, okay, let's suppose there is some data to be pushed, and then you have not pushed it to application layer, and suddenly you get this data, okay, suddenly you get this data, then will you push it out of order, or will you push it in order only? So you will always push in order. It is just that whenever receiving this data, it is just that you are saying, okay, let's just push this whole data to application layer immediately, right? So push means that push at the sender side and push at the receiver side also. And there is one more flag, that is URG flag. URG flag. Okay. If URG is one, it means that some data is urgent. And from starting sequence number to sequence number given in urgent pointer field. Okay, so from this data to this data is urgent. I mean, from the starting sequence number to the sequence number field. So which means, let's suppose this is the segment I'm sending. I will say from here to maybe till here, this data is urgent. What does the urgent mean? We will come to that, but we will determine first that what is the urgent data in this segment, and how to get this last bit using the urgent pointer field. What is the urgent pointer field? See here. So here in the TCP header itself, you will be having a urgent pointer field. So it will tell you that that what is the last byte that is urgent. I mean, from starting to this byte till this byte, the data is urgent. Okay. So basically, if URG is 1, it means that in the segment itself, from this byte to this byte, this data is urgent. Now, what do I mean by saying the data is urgent? Does it mean that that at the receiving side we are sending the out of order data, which means if this data is urgent, let's suppose at the receiving end, this is the data that I want to send, okay, to the application layer, and I suddenly got this data. Will I send this much data immediately? Does this mean that I'm sending the out of order data? So basically, first of all, this URG is never being used, but it doesn't mean that we are sending the out of order data. Okay, we always deliver in order data. It just means that from here to here, something is urgent. Okay, and what does this urgent mean? I mean, as a human, it is just like a good name. Urgent may not be very good name. It may be some, like we could have some other name for this, but yeah, urgent means that like it is some special treatment might be required. Okay, from here to here, and then this is some normal data, some normal. This is some urgent data that I have. Some special treatment might be required, and what is the special treatment? It depends on the receiving end. So we just leave it to the receiving end that how to treat it especially, but it never means that we are sending it out of order. See, I mean, if you go to the books also. So this is one common misconception that that people think that we are sending the out of order data, but it doesn't mean that we are sending out of order data. See here, urgent data. In the urgent data, that the sending application program tells that sending TCP, the piece of data is urgent. The sending TCP creates the segment and insert the urgent data at the beginning of the segment. The rest of the segment can contain the normal data from the buffer. The urgent pointer field is the header, defines the end of the urgent data, right? So for example, this is the example. Now, it is important to mention that TCP urgent data is neither priority service nor out of band data service that some people think. Okay, it is also written in the book that it is not out of band data service or some priority service, something like that, right? And then what is the urgent data then? If it is not out of band, if it is not priority or something, rather TCP urgent mode is serviced by the application program at the sender side, marks some portion of the byte stream as needing special treatment by the application program at the receiver side. So we are just saying that this requires a special treatment. And what is the special treatment? That is left to the receiver. The receiving TCP delivers the byte, urgent or non-urgent, whatever it is, and to the application in the order only. There is nothing out of order here. Okay. So this is common misconception. In fact, like book generally do not write these things, but in book also it is written that some people think like that, right? But it's not in that way. Okay, then what is urgent? But it informs that application program that the beginning and end of the urgent data. It is the beginning of the urgent data and this is the end of the urgent data. Now it is important. See here, it is left to the application program to decide what to do with the urgent data. Okay, so we are not saying that it is some priority data or it is some out of band data or something like that. We are leaving this to the application program at the receiving end, that how to do, what to do with this urgent data. Okay. So basically, in practice, if you look at the cross, in practice, it is clearly written there, this URG flag is never being used. Okay, but in theory, it like this has been designed just for some special purposes that we are not using it currently. Okay. Anyway, I think there is no point in spending much time in the URG flag because it is not being even used. Yeah, we can never send out of band data. Yes. Okay, there is no facility because TCP always send in band data, which means in order. Okay, now see here, it is clearly written that it is not out of band data, neither it is some priority data. I have also highlighted it. Okay, now I think there is one last flag that is remaining, which is RST flag, I think, right? Okay, RST and fin flag. RST flag is some flag which is used to reset the connection. If let's suppose there is some connection that I want to reset because of maybe some problem, then I will set the RST flag, and then all of this SYN plus ACK and ACK will happen all of over again. Okay. So case is saying what will receiver TCP will do to prioritize. To prioritize means you want to send out of order data. You cannot send out of order data. Okay. So no, there is nothing out of order data. Once if you are, I mean, at the sender side only, you need to take care of that. If you have sent something that has already been sent, now if you want to send something, then which is urgent, then send it as soon as possible. Okay, so that, I mean, you are going to deliver is in order only, but you send it as soon as possible so that it gets delivered as soon as possible. Okay. So RST is used to reset the connection. Now, maybe I think it is a good time to see the fin flag, right? So TCP connection is over. See, this is the sequence number I'm sending. Initially it is SYN, and for initial packets, this is SYN, this is SYN. Now the sequence number is 8000. It will consume one sequence number, so the ACK is 8001. And then this sequence number is 15,000. Then it will consume one sequence number. It is 15,001. Something like this. Now there is something called a window size also. Okay, I mean, I might talk about the fin, I think. Okay, so I will talk about the fin, but in just one slide. But before that, let me tell you one more field, which is called window size. See here, it is a window size. What does this window size mean? If I'm at the sending end, then which window size I'm telling? My window size I'm telling, or I mean, I'm telling the opposite window size. Which window size do you think I'm telling? If I'm sending some data, can I tell the opposite window size, whatever the whatever the other party is having? Obviously, I cannot tell, right? I can only tell my window size, and I'm just interested to tell the other party that this is my receiving capacity. Okay, so this is always an advertising window, which is also called receiving window. So I always advertise the receiving window. That, see, this is my receiving capacity. If you want to send the data, then please do not send me data more than these many bytes. Okay, this is always my window size, which is also the receiving window size at my end. Got it? So see here, I'm here. If I'm sending some data, then I'm saying that, okay, my receiving window size is 5000, which means if you want to send me some data, then please do not send me more than 5000 bytes. Okay. And similarly, it is saying if you want to send me some data, then please do not send me more than 10,000 bytes, something like this. Right? Great. Now let's just go to connection termination. I think you have already seen this. Fin is the first packet that we say that, okay, for that we this client want to terminate the connection, and then this server will say that if the server also wants to terminate the connection, it will say that fin. If it doesn't want to terminate the connection, it will say only the ACK, right? I hope that is clear. See, if it is fin, it might send only the ACK. In between, there will be a data transfer. It means the server still has some data to transfer. So that's why it could be either 4-way or it could be either 3-way. Yes, Sumant. Tell me, what is your doubt? So in the connection termination, let me go here. For the connection termination, you have fin. Sorry. You have fin where you are saying that you want to terminate the connection. And then now it depends on the server. If it wants to terminate the connection, then it will say that, okay, I acknowledge your packet, and I also want to terminate the connection, right? And then it will say, great, let's just terminate the connection. So this is 3-way. It could be a 4-way. 4-way means that it will say that, okay, see, I want to terminate the connection. Then it will say that currently I don't want to terminate the connection, but I have just received your packet. Let me send some data. Okay, let me send some data. And then after it will say that, okay, like once it receives the acknowledgement for this data, it will say that now I want to also terminate the connection. It will say that, okay, great, let me also terminate the connection, right? This is 4-way. 4-way means you are exchanging 4 packets, 1, 2, 3, 4. This is 3-way. Okay. So what is the doubt? Client already terminate. How ACK has data to send in the last? No, client terminate means that I'm not ready to send any data. It just means that it doesn't mean that I cannot send the acknowledgement. Obviously, the acknowledgement it has to send. It just means that now I will not be sending the data. If if you have allocated any buffer or anything at your end, so obviously at this end there will be a receiving window, right? A receiving buffer or receiving window. It is just saying that you just free up all the resources that you have allocated because of me only. Okay, I will not be sending any data. Obviously, it has to send the ACK. Okay, it doesn't mean that that it has shut down. If it is shut down, then how can it send the data? How can it send the fin plus ACK like this, right? Okay. Oh, no, this is wrong. Okay, this is wrong. No, I think I just did it unintentionally. So it means like here you cannot send the data. In this ACK you cannot send the data. Okay. So whenever you have sent the fin, after fin you cannot send any data. So it is actually wrong. Okay. I mean you can correct it. Okay. So you cannot send the data. I'm 100% sure. Like once you have sent the fin, you cannot send the data. So you can correct it. Now this is called connection termination. Could be a 3-way or could be 4-way, I think. Okay. Okay. It is a 4-way. Now let's just see that I mean how the TCP is basically doing the some exchanges, maybe the flow control. So maybe we will see flow control with some examples. Yeah. So these are some examples of the flow control. And before that, let's just see some states in which in which the TCP can go. So this is some state diagram which is saying that initially it is active open. Let's suppose it is active open. It is saying that I want to establish some connection SYN, and then like this is just some names, nothing very fancy. These are some names which is saying that okay, I want to establish some connection. And then once it sends the SYN packet, it is now in the SYN sent state. Okay, these are some states: SYN sent, established, fin weight 1, fin weight 2, like that. Okay, a very easy state. I mean the name, by the name itself it is very clear. SYN send means you have sent the SYN. Now it is initially in the listen state. It will say that okay, SYN received. The moment it receives the SYN, it is in the SYN received state. Now it will send the SYN plus ACK. Then once it receives the ACK, then the connection is established, right? So once SYN plus ACK is received at this end, then the connection is established at this end. When the ACK is received at this end, then the connection is established at this end. So there is a data transfer. Now suppose that after the data transfer it wants to terminate this connection, then it will say that okay, I want to terminate the connection. Then fin wait 1. Fin wait 1 means that I have sent my fin. Okay, I have sent my fin. It is waiting for the acknowledgement. Then once it gets the acknowledgement, it will say that okay, now I'm waiting for your fin. Fin wait 2. It means I'm waiting for your fin. And then close. It will, once it acknowledge that okay, that you don't want to send me any data, then it will say that okay, close wait. I mean this is just some state name. It means that I have closed. Maybe close wait means that I have closed the connection from one end, basically. Like I will not be getting any data from your end. And then it can send the data and acknowledgement whatever it is happening. It is in the fin wait 2 state. And then after it will also send the fin, and then it will say that okay, I also want to terminate that. Then it is in the time wait state. These are some state names. And then once it receives the ACK, it will be the close. Okay. So in fact, like there has been some question that has been asked on Gate based on this. Maybe let me just, yeah, maybe you can answer this question now. Identify the correct sequence in which the following packets are transmitted on the network by the host when a browser requests a web page from a remote server, assuming the host has been just restarted. So what is the first request that you will be doing? DNS, right? And after DNS, will you be doing HTTP? Yes. After DNS, there will be TCP, right? I mean, once you establish the DNS, I mean, once you get the address, first step is to establish the connection. Once the connection is established, then I will tell you in the application layer protocol that how HTTP is basically transferring the data. But once the connection is established, then you will transfer the data. So maybe DNS, then TCP SYN, and then HTTP. Yes. So I think C should be the answer, right? Yeah. C is the correct answer. First, you send the DNS to get the IP address, then you establish the connection with the IP of Google using TCP. Finally, okay. So C is the correct answer. Now, I was talking about some questions that they have asked related to the states. Yeah, maybe this question we can see. So they are saying the three-way in the three-way handshake, this happens. Now, first tell me if it is sent some SYN, then maybe it will be the SYN sent. Okay, I mean the state might be the SYN sent. So they're asking which of the following is true. So let's just see which of the following is true. S1 is saying loss of SYN plus ACK from the server will not establish the connection. Tell me, is this correct option? If this packet is lost, then there will be no connection establishment. Yes, that is true, right? I mean, if this packet is lost, then okay, then the server will say that I'm ready to listen since you are ready to send the data. I'm ready to listen, but this client will never get to know that if the server is ready to listen. See what is happening. If you send the SYN packet, suppose this is lost, then it will be in the SYN sent only, right? This client will never get to know that okay, the connection is established. Once it receives the SYN plus ACK, then only the client will send the okay, the ACK has been received, now it will establish the connection, right? Similarly, at the server side, at the server side, whenever it is sending the SYN and then it receives the ACK, then only the connection will be established. So connection will be established after the SYN and ACK pair. Okay, just using SYN, you cannot establish the connection. SYN and ACK, then it will say that, okay, connection is established. It means at least I can send the data. Okay, at least I can send the data. And now it is, if let's suppose it is also receiving the SYN and ACK from SYN, and then it is sending the ACK, then it will say that okay, now I can also send the data, something like this. So connection is established only after SYN and ACK pair, right? So loss of SYN plus ACK from the server will not establish the connection. So this is true, right? What about this loss of ACK from the client? Loss of ACK from the client cannot establish the connection. Tell me, is this true or false? If this ACK is lost, then the connection is not established. See, if this ACK is lost, then this server will be in just SYN received state, right? I mean, server will not be in the connection establishment state. But to transfer the data in TCP, it is forced. Okay, it is not like we can just establish the connection at one end. It is forced that we should be establishing the connection at both the ends. Connection established means that both are in the establishment phase. Then only the data transfer could happen. If this is in the SYN received phase only, then the data transfer cannot happen. So if any of this packet is lost, right? If the ACK is also lost, then also you cannot establish the connection. It is actually forced to have the full duplex. It's not like that you can just establish the connection at the one end. Okay, so that's why this is also true. Why? Because if this ACK is lost, then it will be this just in SYN received state. It will not establish the connection, and the data transfer can only happen when both are having the connection establishment state. While sending the data, it can set the ACK one. Which one? No, it has sent the ACK, and then yeah, here also you can send the data. It's not like that. Here also you can send the data. It's not the compulsion, but okay. Can you send the data here? This is the first question. Can you send the data here with this ACK? What do you think? See, let me just tell you. See, an ACK segment, if carrying no data, it does not consume any sequence number. So basically, it can carry the data. Here itself, it can also carry the data. I mean, you can carry the data here. Where is this, right? Yeah, you can carry the data here. That's not a problem. So what it is saying, loss of this ACK. No, loss of the ACK cannot establish a connection. That is true, right? I mean, loss of ACK, it may carry the data, may not carry the data, but it cannot establish the connection. So for the connection establishment, all of these three has to happen. See, answer is a B. B means S1 and S4 only. Okay, they're saying S2 is not true. I think it should be true, right? If this ACK is lost, cannot establish the connection. Okay. Loss of the ACK from the client cannot, no, this is not true. If after ACK client immediately send the data, then everything. Okay. So they're saying that if you're sending this ACK, even if that is lost, yeah, okay. So what they're saying, let's suppose that you are sending, I mean, actually for the connection establishment, all of these three should be happening. But suppose this ACK is lost. Okay. Suppose this ACK is lost. Then in this case, let's suppose this client doesn't know whether the ACK is lost or not, and server obviously cannot get to know what is happening. But suppose this ACK is lost, and then client is basically in the impression that this ACK has been received. Then after it is sending some data, and obviously it will be sending the ACK, the same ACK number that it is expecting next. Now since this ACK is lost, but this ACK will work for you. That's what they are saying. That even though this ACK is lost, but if you're whenever you're sending the next packet, at that time you will also be sending the ACK. That this is what you're receiving, you're expecting that ACK field. So that packet will serve as ACK. That's what they're saying. Even if this ACK is lost. So it means that you can send the data, right? Okay, you can send the data, but server cannot send the data. Currently, server cannot send the data. Client can send the data because client doesn't know that ACK is lost or not. So client can send the data, and with this data, it will send the ACK. But can server send the data? If this ACK is lost, then tell me, can server send the data? Let's suppose it has not been received. Can server send any data? No, right? So server cannot send any data. Yeah, but if it is lost, then client can send data. Because client will think that okay, that has been received, and in the data again there will be some ACK. So client can send any data or any request, right? In generally it is HTTP. Let's suppose it is HTTP request. Get request. Okay, so let me see the routes. Sender while sending data, it can send ACK also, right? Connection is established on the client side. So if the client sends the data, connection be established on server side too. Yeah, that is correct. So server cannot send the data meanwhile. Server just go to establish state when the ACK sent. Okay. So yes, I mean connection is established or not. That is I am still in doubt because server cannot send the data. I mean generally it is not the case that server wants to send first. Obviously client will be having some query that the server will be replying. So generally it is the case that client will be sending the data only. I mean after this case, then server do not send anything, because until and unless client asks something, how can server send, right? I mean server is just here to help us, but client should be asking something. So there will be some get request. Okay, client will be asking something, then only server will be replying. So generally that's the only way that client generally request, and server do not upfront send anything randomly. Obviously it cannot send any random data to you. Once you request something, then only it will be sending. So generally client requests something and then server replies. So yes, server cannot send the data, that is true, but it is also true that server does not even send the data. I mean generally server do not send any data without any request. That's also true, right? Server cannot send the data, but it generally also do not send the data. So, okay. I don't know, maybe we can keep it as a connection establishment. So see, these things are again, I'm not sure if it is well defined or not. Okay, I need to check this link. I'm not sure if it is well defined, but again, these things could be on just luck. Okay, I mean, you might say that this S2 is false. Okay, oh sorry, S2 is true, and let's suppose this is true, this is true. So, and let's just read this S3 and S4, then we will get to know if there is any option matching. Okay, so what is S3 saying? Server moves from listen to send receive. Yeah, initially it is listening. Yeah, right. And then send received, then send sent, and then establishment. In the state machine on no packet loss. So see, is it correct? It is listen, send receive, establishment, right? So listen, send receive, send sent. Okay, this send sent is not there at the server side. It listens. The moment it receives send receive. Okay, send sent is not an state in the on the server side. So that's why this S3 is false. It is just SYN received, and then it sends this. After the SYN is received, it will be in the SYN received state. Okay, not in the SYN sent state. And then it immediately send this, and then it will be waiting, and then this is the establishment. So the SYN sent is not there. Listen, SYN received and establishment is there. So that's why this is false. What about this? The server moves from listen to SYN received. Yeah, that is true, right? So do you have any option where S1, S2, and S4 are true? Since there is no option, so maybe if I go with the best one, I'm saying S1, S2, and S4 are true. So maybe you can say S3 is false. So that's why this is not true. This is not true. Maybe between B and D, we need to select, right? S only, they're saying only S1 and S4 or S2 and S4. Yeah, okay. So anyway, like we need to check whether it is very well defined or not, because here the doubt is that the connection is established or not. It depends. I mean, server cannot send the data. So can we say the connection is established? That's the only confusion, right? Okay. Currently, you can take it as a false. So that's why the B is the answer. But we need to look at this link maybe more carefully. So you can just go to this link and then see if there is some solid proof there. Okay. Or maybe let me just go to that link. This is what if TCP handshake segment is lost? You can see my screen, right? So, okay, there's the same link. Now, what they're saying in TCP three-way handshake, 3 segments will be sent. And what if the third segment ACK is lost? And how do two hosts know the segment is lost? Okay. So TCP has a sequence number in all the packets. Hence, it is easy to know if the packet is lost or not. If a host doesn't get an ACK, a packet is just resent. ACK on the packet, he just resent it. So in most cases, though, even if the ACK was lost, there will no responding for very simple reason. No resending for the very simple reason. Directly after ACK, the host has opened the TCP protocol is likely to start sending the data. See, they are also saying it is likely, right? Likely to start sending the data. I mean, the client generally sends the data upfront. Server do not send the data. So it is likely that it will start sending the data. The data will as all the TCP packet has the ACK number, so the recipient will get the ACK in that way. I mean, it will anyway get the ACK in the next data that client is sending. Hence, the sender, the SYN ACK should reasonably not care that if didn't get the ACK, because it gets an implicit ACK in the following package. So again, these things are quite debatable, I think, because they are also saying reasonably not care. I mean, they are not saying that very solid statement just for the examination purpose. I mean, these just for the practical use cases, right? Practically, reasonably, I should not care. Practically, I should not care if the ACK is lost. But for the exam, what should we consider? That's what the question is. The resend of SYN ACK is not only necessary. The resend of the SYN ACK is only necessary if there is no data is received at all. Okay, so if the client is not sending neither ACK nor data, then obviously you will be sending the SYN ACK again. Now there is RFC that is saying if our SYN has been acknowledged, perhaps in the incoming segment, the precedence level of the incoming segment must match the local precedence level exactly. If it does not, reset must be sent. It does not, a reset must be sent. In other words, if the ACK is dropped, but the next package is not dropped, then everything is fine. Otherwise, the connection must be reset, which makes the perfect sense. Yeah, it is again like it is making sense or not. Okay, so yes, it is making sense. As I said, like it is making sense to not care about this ACK loss, but for the examination purpose, what should be the answer? That's the question, right? In the examination, things should be well defined, not just for the practical use cases. Yeah. Is my voice better now? It should be better, right? Okay, comparatively. So sorry, you should have told me. No worries. I think we can continue. Okay. So anyway, like let's just move further. For this question, we will just leave it here as it is, because for the practical purpose, as I said, it does we don't care. But for the theoretical purpose, the thing should be well defined. Okay. Let's see this question. This question has been asked in GATE 2017. What they're asking is that consider a TCP client and the server running on two different machines. After completing the data transfer, the TCP client calls a close to terminate the connection, and the FIN segment is sent. So you are sending a FIN. So after FIN, I think it goes to FIN wait 1, right? Server side response was sending an ACK, which is received by the client side TCP. Okay, it is sending only ACK, not FIN plus ACK. Then I think it goes to FIN wait 2. As per the TCP connection diagram in RFC 793, in which state does the client side TCP connection wait for the FIN from the server side? So now it is waiting for the FIN. In which state it is waiting? I think answer is FIN wait 2, right? So see, it is FIN wait 1, and then in the FIN wait 2, it is waiting for the FIN. Now, once this FIN comes, then it will say that, okay, time wait. After some time, basically, that I will tell you that what does this time wait mean? Okay, when we talk about the TCP timers, I mean, immediately it does not close the connection. After some time, actually, it closes the connection. Okay, I will talk about this time wait later. That what does this time wait mean? Apart from this, like I think everything else should be clear, because these are just states. And why I'm keeping some time before the closing the connection, it is a good question that we will answer later. Okay. So when I talk about the TCP timers, so I think the answer is FIN wait 2. Yeah, I also think so. It's like you might need to remember it, or maybe this FIN wait 1, FIN wait 2 are very easy in SYN side. I think this client side is obvious. I mean, now I think I also remember it. And at the server side, you may just remember that there is no SYN sent here, just SYN received, and after it goes to this. I mean, maybe you need to remember it. There is no other way, I think. Okay. So they have not asked much question from this diagram, but since they have asked 2 questions, so I think it was a better idea to do those questions whenever we were doing the diagram. So here the answer is D. Yes, FinWeight 2. Anyway, the answer is D, right? Okay. So now let's move further. Yeah, again, this is the same diagram that I have taken from another book. So in this diagram, they have represented using this circle. In this diagram, they have represented using these. Okay, both diagrams are good. So you can refer any one of them. See, this is close wait or there is time wait. Time wait is some state in which the second fin is received and the ACK sent waiting for 2 MSL timeout. So what is this 2 MSL timeout? This is I will talk about it in the TCP timers. Okay, so this is something related to the TCP timers, the time wait state. Now let's talk about the acknowledgement in TCP. So ACK segment do not consume the sequence number and are not acknowledged. So basically, whenever you are sending only ACK, they do not consume any sequence number. But there is a question like how to send the ACKs, right? I mean, whenever the ACK is first of all the cumulative. So ACK is cumulative. But whenever it is cumulative, there is always a question that how to send. Maybe the question is that maybe after some timer. Someone can say, let's not worry about the time. Maybe let's worry about after some packets. Okay, let's suppose after every 3 packets I will send. After or maybe after some for example 5 packets. Okay, 5 packets. After some packets I will send the ACK. Or maybe you can say after some timer, after some packets. I think these are the only 2 possibilities. Maybe you can also say that if I'm receiving something out of order, then I will send the immediately. I will send the ACK immediately. So TCP follows this flow diagram. So basically, I mean, whenever you are receiving some data. Okay, so let me talk about it here. Whenever we receive some data, I mean, we means a receiver. Okay, whenever receiver receives some data, then it does following to send ACK. Okay, that's how the ACK is sent. How? It will first check whenever it receives the data. It will first check, do I have the data to send? Do I have? This is the first step, data to send. If it is having some data to send, then obviously it will send the data, and obviously the ACK will be piggybacked, right? Piggyback means like it will send the ACK simultaneously. I mean, in the data only. So it will first say that, okay, do I have some data to send? This is the first question that the receiver will ask to himself, that do I have some data to send? If the answer is yes, okay, if the answer is yes, then will I send the ACK or not? Tell me. Obviously, I will send the ACK immediately. There is no need to wait for any timer or something, right? So there is no need to wait for any timer in this case. Okay. Right. So if I have some data to send, then I will say yes. Then I will immediately send the ACK. Also send ACK with data. I hope that is clear to everyone. Now, if it doesn't have any data to send, let's suppose no. If it doesn't have any data to send, then what it will check? It will check that since it has just received some data, right? I mean, it has just received some data and it wants to acknowledge it, right? So let me go to the next page. Now, if it doesn't have any data to send, then it will check that whatever I have just received, is this out of order? Okay. See, I want to send some ACK. Why? Because I just received some data, then only I want to send some ACK. So whatever I have just received, is this out of order? So maybe, yeah, in order or out of order, you can just ask this. Like whatever I just received is in order. Okay, if it is in order, if the answer is again yes, if it is in order, it could be no also. If it is no, then it means that okay, it is a it is out of order data. It means that I will immediately send the ACK. Okay, immediately send ACK. That's how TCP behaves. It will check whether it has data to send. If it has data to send, it will obviously send the ACK. If it doesn't have data to send, then it will check that okay, do I have in order data or out of order data? If the data is out of order, it will immediately send the ACK. If data is in order, then it just applies the algorithm, which means maybe it will wait for some timer, it will wait for some packet, something like this, right? So if it is the in order data, then either waits for the timer or maybe 2 segments to come, something like this, right? Then maybe wait for the timer or something like this, right? Let me write wait for the timer, then it apply the algorithm. Is this flowchart clear to everyone? It is very important flowchart that how TCP is actually sending the ACKs. Okay, so TCP, yeah, I can call it TCP ACK flowchart. Cool. So now let's move to the next slide. I hope that these things are clear, that what do I mean by fast retransmission. TCP also does the fast retransmission. It means that whenever you are sending some data, if the packet is lost and then you are sending some packet, since it is out of order packet, it will immediately send the ACK, right? It will immediately send the ACK. And once you receive the 3 ACKs before the timeout, then you will say that, okay, I think the packet is lost. Then you will immediately retransmit. That's called the fast retransmission. Okay, that's what TCP follows. So basically it says that do not only wait for the timeout, you can also if you are receiving the 3 ACKs, 3 duplicate ACKs basically, then you will immediately send that packet. Now what do I mean by 3 ACKs? Why not 4? Why not 5? Why not just 1? Why not 2? Like see, 4 or 5 will be too long of wait. Maybe by that time the timer will expire. And why not just 2 then? Maybe 2 is too early. Maybe the packet must have got delayed. Maybe I do not need to retransmit. So it is just a heuristic number. Heuristic means just by the some practical purposes we have taken the 3. Have you understood that why we have taken 3? Because 4 or 5 will be too long to wait. By that time timer will get expired. And then 2 or 1 will be too short to wait, because maybe the packet is delayed and maybe I do not need to retransmit. Maybe it is just delayed and it will automatically get received. Right? So that's why they have just taken heuristically, they have just taken 3. There is no mathematics behind it. Okay. So now let's just see some operations, which is also called flow control. Okay, these are some flow control operations, that how TCP is basically behaving. Currently, I'm not having any congestion here. Okay, these are just flow control operations. So initially, you are saying, let's suppose that your sequence number you're sending from here to here, ACK is this. So based on that, it will basically send some data and all. So it is just a very normal operation. There, even I have not talked about any flow control window. Okay, so very normal operation. It is sending some sequence number from here to here and saying that, okay, I have received and I'm expecting this. It will send some and it will say that, okay, I'm expecting now this, something like this. And then there is something that is happening. Now, suppose that this packet is lost. If this packet is lost, then maybe, okay. No, this packet is not lost. Yeah. So this is ACK timer. This is timer for what? That's why I'm just wondering. Okay. Yeah, see here that what is happening, that you are receiving this packet, then maybe if you do not have any data to send, then maybe you will wait for some timer. Okay, and once the timer getting expired, then you are sending the ACK. Right, after some timer you are sending the ACK. Then it is, let's suppose it is having some data always to send, then it is sending some data. And then let's suppose you are still not having any data to send, then after some timer maybe you will be sending. But let's suppose in between you receive something, you receive some data, and then probably you might have any algorithm. So maybe you will say that, okay, this timer is lesser than 500 millisecond. Maybe you're sending the ACK, which is cumulative here, which means that this is saying that I have received the two packets. And this ACK I'm sending after the timeout. Maybe because I do not have any data to send. That's why I'm waiting for the timeout. If I'm having always data to send, just like a server, then I will be immediately sending the ACK with the data. Okay. So let's see this. Client is sending something, and then receiver store this. Client is acknowledging it, and then receiver, this client is again sending something which has been lost. But client is sending this, then receiver is receiving something which is out of order. So it will say that I'm expecting 701 only. Okay. And then maybe after some, this is called the retransmission timeout. Okay, just a timeout that we have. Then after some timeout, I will say, okay, let me just resend this packet. And then after you resend it, then it will be in order and it will just acknowledge it using the last sequence number that it is expecting. So 901 now it is expecting, so it will say 901, right? So I hope that is clear. Very, very easy diagrams. I mean, it has received this, and then it is ACK, then it has been lost. So there will be a timer. After timeout, you will be sending it again, right? So this is basically resend after timeout, and maybe there could be a resend after 3 ACKs also, which means if this is lost, and then you keep on sending, obviously, if you have some data to send, you keep on sending, and then there will be a timer. And then once this timer expires, then you will be obviously sending it again. But before this timer, if you have received the 3 duplicate ACK, then you are again transmitting it. That's called fast retransmission. Okay, fast retransmission means sending something before the timeout. Okay. So if ACK is lost, then let's suppose it's sending something, then there will not be a problem because it's a cumulative ACK. Then maybe again, like at this point in time, I'm receiving it. So if ACK is lost, then it is not a problem because it is cumulative ACK. Anyway, these kind of the similar operations that we have earlier seen in the data link layer. Let's suppose if this ACK is lost and maybe it is sending something, and then after this packet, it is receiving the cumulative ACK. If let's suppose it does not receive this ACK, maybe then since the ACK for this packet has not been received, so it will be retransmitting this packet after the timeout, right? Okay. So now let's just see the TCP flow control, that how the TCP flow control is happening. So suppose that you initialize some sequence number, and then you say that, okay, I'm sending with the sequence number 100. And then at the client side and at the server side, there will be 2 windows. But currently I'm just showing you, I think only one window, which is this is the sender window at the client side. At the receiver side, there's a receiving window, but there are 2 windows. Okay. I mean, at the client and the server, there are 2 windows. So I'm currently treating this client as a sender and server as a receiver. But yeah, there are 2 windows always. Okay. So there is a sending window. So I'm sending something, and let's suppose I have sent some data, just a sequence number 100 initially, and then I'm ready to send from 101 to 800. So this is my window that I'm ready to send. So once this connection is established, now I will be transferring, right? After this 3, I will be transferring. So suppose I transfer some data which is of 200 bytes. So which means that I have sent this area I have sent. If I've sent this, it will receive this and it will say that, okay, now it is expecting 301. Now it is very interesting. Now just see here, it will advertise its window. Okay, so maybe let me go to new page. See what is happening. Let's suppose this is sender, this is receiver. Okay, I'm talking about TCP flow control, how the TCP flow control is happening. Now, let's suppose there is SYN packet initially with the sequence number is 100. And then this is SYN plus ACK. It will also be having sequence number, which is suppose, I mean, let me take the same example, which is suppose 1000. Okay, suppose this sequence number is 1000, which means the initial sequence number here is 100, initial sequence number here is 1000. Now it is sending ACK. Okay, now suppose after it I'm just having some data transfer. So this has been done, suppose. Okay, so suppose that this has been done, and now I'm doing some data transfer, which is between sender and receiver. Now let's just see what is happening in the data transfer. So I will send my first packet saying that I'm starting from 101 because 100 sequence number has been consumed, and then it will also say in this SYN plus ACK, it will also say that what is the receiving window. See, I'm also saying the receiving window, which means like if you want to send me some data, then I have advertised my receiving window to 800. Then I'm saying that okay, if you want to send me data, then do not send me more than 800. And I am saying to this receiver that do not send me more than 2000. Okay, so currently for our purpose, this receiving, I mean from left to right, this receiving window is not very useful because it is not sending anything anyway. But let me talk about it. So suppose I'm saying now the receiving window is 800. Okay, and now I'm saying the receiving window here is 2000, which means that whenever I'm sending a SYN packet, I want to establish some connection. Now whenever it is accepting some connection and also wants to establish some connection from its own side, which is forced because it is full duplex. So it will say that okay, see, I have accepted your connection, okay, and I'm also establishing a connection. I also want to send some data. I have accepted your connection. I also want to send some data. It is what it is saying. Since I have accepted your connection, and if you want to send me some data, please do not send me more than 800, right? It will say do not send me more than 800. Then it will say that okay, thank you for accepting my connection. And then it will also say that if you want to send some data, do not send me more than 2000. That's what they're saying. Initially, it will not send the receiving window side because there is no point in sending the receiving window side. I mean, initially, if you want, you can send the receiving window to with 2000, but there is no point because you don't know whether the receiver will listen to your request or not. Once the receiver is acknowledging that okay, it is ready to accept your connection, then only you will sending okay, please do not send me more than 2000, something like this, right? So anyway, it has advertised initially, it has advertised receiving window to be 800, suppose, okay, which means that if you want to send me something, do not send me more than 800. This is what it is saying. This is the sender, this is receiver, okay, currently. Now it is saying do not send me more than 800. Now you will say okay, starting from 100, I mean 101 to maybe last is, if it is 800, then I think it will be 900, right? So from here to here, probably, right? So basically, let's suppose these are the 800 bytes till the 900 or till 901. I think, I mean, starting from 101, if you add one, then there will be 2 bytes. So basically, if you add 800, yeah, so I think till 900, right? So it will be sending 101 to 900. So it will say that okay, I can send. Sender is saying that okay, my sending window is this 101 to 900, which means I can send from 101 to 900. This is what it is saying. Because receiver is saying that I can handle 800 bytes in one go. Now tell me, will sender send all of this immediately? See, receiver is saying that I can handle 800 bytes in one go. Will sender send all of them? All of the 800 bytes? What do you think? Actually, it can send if it has the data. But suppose it do not have the data. I mean, currently, let's suppose it doesn't have that much data to send. It is saying that, okay, I just have 200 bytes to send. Okay, suppose it is saying that, see, you can handle 800 bytes. That's what I know. But I just have 200 bytes to send. So it is saying, see, I'm just sending 200 bytes. So which means that it will say the sequence number is 101 that I'm sending, and the total length that you can calculate from the IP header. So basically, it is sending the 200 bytes. Now it will say that okay, now my window which was capable of handling 800 bytes, okay, which was capable of handling 800 bytes, 200 bytes you have sent. Now suppose that I do not have any increment in my window, then it will say that, see, I'm acknowledging your packet, okay, and then it means that it has sent till 200. Now I'm basically expecting 301, and now this time my receiver window size actually has been decreased, which is just 600. Okay, you're getting my point? So it is saying that okay, I'm sending some 200 bytes. Now it will say okay, I'm acknowledging 200 bytes, but now if you want to send next, then do not send me more than 600. That's what it is saying.
Now sender will say that, okay, I will not send more than 600, which means these are the 600 bytes that I can send if I have the data, but it depends whether I have the data or not, right? See, so it is saying that that you can send 600 bytes. Now it will say that, okay, these bytes have been acknowledged, and then I can send this much data. But suppose I do not have that much data, I just have next 300 bytes. Okay, so which means, so this is 300 till 300 I have sent. Now from 301 I'm sending next. Okay, so now from 301 to 900 I could have sent, and this is what I have already sent, 101 to 300. This is what I have already sent. Now this much I could have sent, because that's what the receiver is asking to send. But let's suppose this time I only have 300 bytes to send, maybe till 600, right? So suppose this much bytes I'm just sending. So it is saying that, okay, now this time I'm sending a sequence number with 301, and now my window is just I'm just sending you 300 bytes. So it will say that, okay, I've accepted your packet, which means I'm now expecting the next byte, but maybe the receiver window size. Okay, can anyone tell me what is the receiver window size here? It was initially 800, but 200 you have sent, then it was 600, right? And then you have sent the 300. So 200 you have sent, then you have sent the 300. What is remaining? 300 is remaining. So can anyone tell me the receiver window size? It should be, should it be 300? Not necessary, right? I mean, the receiver window may expand, right? It will say that, see, now I have the more space, maybe because this 200 I have transferred to the application layer. Now my buffer is having more space. If you want, you can send me maybe 800 again. Okay, it depends. I mean, it depends on the space. It is not necessary that I just have prefix 800, and then once the 800 I have sent, then receiver is not expecting anything. No, it's not like that, right? So receiver window size could be anything, irrespective of what you have sent, what was earlier. Okay, it could be anything. Anytime these numbers could be anything. So let's suppose the receiver window which I'm sending now this time is, let's suppose, is 400. Now I'm saying that, okay, I'm expecting 400 bytes. Now once you send me, maybe you can send me at most 400. Now let's suppose that from 601, yeah, you can send me at most 400. It is saying you can send me at most 400, and then after some time it is saying that, see, I have a good news, you can send me now 600 also. Okay, now sending window size will get expanded. Okay, the question is that server will not send the data to the application till the window is full. No, it's not like that. Server is not, it doesn't wait for this window to get full. It just wait for some sufficient segments. Maybe the half of the window, maybe 1/4 of the window. Okay, it is not necessary that that this entire window should be full. It is just waiting for some sufficient segments. Okay, just to have some good throughput. I mean, should not be unnecessarily sending every byte, not too much of large segments, right? Not too much of the data. So maybe some midway. So have you understood this? So it is advertising 400, and then sender is saying, okay, now my sending window is 400, but then after some time it is saying that I'm advertising 600. So which means now you can send 600. So basically, this is just a one-way communication that I have shown, which means only the left part is treating, we are treating as a sender, right part we are treating as a receiver, which means whenever left part is advertising this 2000 or something, then this is what I'm not making use, okay, currently, which means like this is not sending. So basically this 2000 and these things I'm not making use, but this is the same way that we do, right? So that's called TCP flow control. Okay, so basically we do advertise some window, and based on that, the sender will send that. I mean, maximum it can send whatever I'm advertising. Okay, and maybe like whatever I'm advertising, it is irrespective of whatever I have advertised earlier. Earlier I might have advertised 400, but after some point in time I'm saying that, okay, I'm advertising 600, right? That is also a possibility. Now This is the flow control, but there is since the TCP is not just I mean hope to hope, it is basically from port to port. So basically this TCP connection is like this. In TCP, it is client, it is server, and whenever you are sending a SYN packet, okay, this SYN packet is not directly getting to the server. There is something called as internet in between, right? I mean, you have the internet here, all set of routers and many things, and then out of those, then you are sending it, right? So that's how it is happening. In TCP, there is an internet in between. Whatever you are sending through the internet. Now, at the receiving side, it will advertise its window, but this internet may not be able to handle that much data, right? So for example, see, whenever the sender is sending, maybe this internet, these routers are not having much capacity, and this is receiver. So so what may be the case, that we need to take care about the internet in the between, okay, in case of TCP. So see here what is happening. See, this is sender, okay, this is receiver. So sender can send, let's suppose, at very high speed, and receiver can also have the enough buffer. It can also receive the data. It has a large buffer, okay, it can also receive the data. But in between, there could be a router which is not able to handle that much speed, or that much packets in just 1 minute, or maybe in just 1 second. It cannot handle that much. It cannot handle that much packets. So that's why there is a congestion in the network. So that's what we need to take care. So sender could be a high-end server or the high-end machine. Receiver could be also the very large buffer, but in between the routers could be having some limited capacity, right? So we need to take care of this. So whenever in the TCP, whenever we are sending something or receiving something, then there is an internet in between. So let's just see that how TCP handles this congestion, and that's what the crux of the TCP actually. Okay. So whenever you are sending some data, then data may be lost, and maybe because of the congestion, it may get lost. Now, suppose if data is getting lost, now as you notice in the previous examples, then it could be lost, and if the packet is lost, then maybe because before the timeout, okay, before the timeout is here, before the timeout only I am sending some data. That's called fast retransmission. If we are sending some data before the timeout, that's called fast retransmission. And what does this mean? It means that this packet is lost, but 3 duplicate ACKs I have received, right? Which means that other packet must have been received. Only one packet is lost, then only I'm receiving the duplicate ACKs again and again. It means there is a congestion, but may not be that much severe. Okay, so congestion may not be that much severe if you're sending some data which is lost, but you are receiving the 3 duplicate ACKs. But let's suppose you are not even receiving the three duplicate ACKs. So let's suppose you are sending something, okay, which is lost, and then whatever you are sending again, that is also lost. Okay, whatever, let's suppose you are sending again, or all of the packets are getting lost. Then, so there are 2 cases basically. One is that if you are sending something, this packet is lost, but this is received, this is received, this is received, and then because of that, you are getting ACK, ACK, ACK. So there are 3 duplicate ACKs, right? This is called 3 duplicate ACKs. Now, because of that, you will say that you need to retransmit the data, and this is called fast retransmission. And let's suppose the timeout is happening at very late. This is the timeout, but before the timeout only, you are transmitting the data. That's called the fast retransmission. Okay. Now, this is one case, but there could be another case where you are sending some data. This is lost, and let's suppose all other packets are also lost. Then obviously there will be no duplicate ACK, and then you will be getting, after timeout, you need to send it. right? After timeout, you need to send. So tell me, where is the more congestion, in the left part or in the right part? Since all the packets are lost, then I will say that is the more congestion. Right? It is less congestion. So there are two cases. One is that you are receiving 3 duplicate ACKs, which means maybe all other packets are received, just one packet is lost. But if you're not even receiving the 3 duplicate ACKs, it means that all other packets are also lost. So this is more congestion. So let's just handle these two cases one by one, right? So TCP basically differentiate in these two cases. I mean, there are different versions of the TCP. Let's just look at them. And that is called slow start and the congestion avoidance phase. So there are two phases in the TCP. In the slow start, what we do, we basically have something called a congestion window that you have, might have already seen. So we start with the congestion window is 1 MSS, right? Or maybe the 2 MSS, or generally it is 1 MSS. You may start with the 2 MSS also. It will be given in the question if that is the case. Or generally it is 1 MSS only. Then what will I do? Whenever I'm sending some data, okay, listen here carefully. Whenever I'm receiving one ACK, see, it is initially just 1 MSS. After one RTT, I will be receiving one ACK. After one ACK only, I will increment this congestion window to 1. Okay, I'm incrementing it to 1 after one ACK. So if I'm sending two packets, then after 2 ACKs, I will increment it to 2, right? Let me go to the page. See what I want to say. Okay. Yeah, see here. Initially, I'm sending, right? Initially, I'm sending one packet. Then once this ACK is received, then I will be incrementing my initially it is CWND congestion window is 1. Once this ACK is received, I will increment it to 1, right? Now it will be 2. Now I will be sending 2 packets. Once these 2 packets ACK is received, okay. Once this ACK is received, listen here carefully. Once this ACK is received, just after one ACK, what is the congestion window size? Can anyone tell me at this point in time? It was 2 here, but after just one ACK here, okay, this is the first ACK. This first ACK. What is the congestion window? It will be 3. Then, because after every ACK, I'm incrementing only 1. Then after this point, it will be 4. Then after this point, it will be 5, then 6, then 7, then 8, something like this. For each ACK, we are incrementing 1. Okay. And the result of this is happening in such a way that it is actually in the power of 2. It is 2 power 0, 2 power 1, 2 power 2, 2 power 3, something like this. I mean, it is increment, we are incrementing exponentially because for every ACK, we are incrementing by 1. Okay, that's called slow start phase. So what is happening here? I'm initially saying that, okay, the congestion may be very high, I don't know. So I will keep it 1. Then I will, after one RTT, I will make it 2. After one RTT, I will make it 4, something like this, right? And after one RTT, I will make it 8. But after every ACK, I'm incrementing 1. That's important. Okay. So now it need to stop. I mean, you cannot keep on multiplying by 2, right? You cannot say 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4 like that. So it needs to stop somewhere. The slow start should be stopping somewhere. Because if you are not stopping it somewhere, then you will be basically sending too much of data in the network, and then there will be too much of congestion, and then you may need to slow down, right? Maybe let's suppose you are coming up with the 64 size, and if you send the 64 size, then maybe the ACK you are not receiving. Then it will be a problem to you, right? So basically, it has to stop somewhere. So this slow start. And what we call it at the threshold. So have you understood this, that how we are incrementing the size of this congestion window? After every ACK we are incrementing, and because of this, as a result, what is happening, that after every RTT you are basically making a power of 2. Okay. So let's do one gate question, maybe related to it, because they have checked this little concept also somewhere. Yeah, let's do this question. This question has been asked very recently in 2018 only. Consider the following segment regarding the slow start phase of the TCP congestion control algorithm. Note that CW stands for the TCP congestion window and MSS window denotes the maximum segment size. MSS, I think it should be there just MSS maybe. MSS denotes the maximum segment size. Okay. So the CWND increases, this congestion window increases by 2 MSS on every successful acknowledgement. Is this true? On every acknowledgement, are you increasing 2? No, right? You're increasing 1. So this is false. Congestion window approximately doubles on every successful. Are you doubling on every acknowledgement? No, right? This is also false. You're just incrementing by 1. Increases by 1 MSS every round trip. In every round trip time, are you incrementing by 1? Again, no, right? You are basically in every round trip time, you are multiplying by 2. The CWND approximately double every round trip. Yes, that is true. So I think only 4 is true, right? So very easy question, but you can do only when you know the concept very nicely. Okay. So C is true here. So I have just copied this question so that, if someone is solving later, then they should not see the answer directly. Okay, good. Now let's just continue. So I hope you understood this, right? In every RTT, I'm incrementing, basically I'm doubling, but in every acknowledgement, I'm incrementing by 1. And this is just a congestion window. But our actual window that we are, that the sender is having, will be the minimum of what can receiver receive and what can network can handle, right? So minimum of both of this. So see here, after 1 RTT, this will be the case. After 2 RTT, this will be the case. Okay. Now let's do one question where I'm saying that that I'm incrementing. So basically here, the after 1 RTT, this is the case and all. But let's suppose I'm incrementing ACK for every 2 segments. Okay, let's suppose I'm receiving the ACK for every 2 segments. Okay, and I'm not receiving the ACK just for 1 segment. So let's do one question where I'm saying, suppose in every 2 segments, then what will be CWND after maybe 3 RTTs? This is the question. Okay. So initially your CWND is 1, and then okay, let's suppose that to start with that start here. Okay, let's suppose I start with CWND as 2. Okay, I mean it will be given in the question. Let's suppose you are starting with the 2. So initially it is 2, and then they are saying that you can send 2 packets, right? Once you send 2 packets, you will be just receiving 1 ACK. Okay, and in every ACK, you are incrementing by 1, right? So you send 2 packets, you will be just receiving 1 ACK only, 1 ACK. That's what the question is saying, that in every 2 packets you are receiving just 1 ACK. Then since it is 2 initially, can anyone tell me what will be after 1 RTT? It will be 3 after 1 RTT, right? Because you are incrementing by 1. In 1 ACK, you are incrementing by 1. That's the rule. See, if an ACK arrives, then CWND will be incremented by 1. That's the rule. Okay. Is this clear to everyone? Now, let's suppose that I'm sending these 3 packets now. Okay. If I'm sending these 3 packets, then what will I do? Then I will be receiving how many ACKs? I will be receiving just one ACK. Right? I mean, there will be one ACK later because of this packet. Whenever the complete 2 happens. But yes, currently I will be receiving just one ACK. Then after one RTT, this is the case. And then after one more RTT, the CWND will be 4, right? Now, suppose I'm sending the 4 packets, 1, 2, 3, 4. How many ACKs I will be receiving now? Because of this one and this one, I will be receiving 1, 2. 2 ACKs I will be receiving, right? So I will be receiving 2 ACKs. 2 ACKs, then this will be 6. 2 ACK, are you getting my point? 2 ACKs you will be receiving, so that's why it will be 6. So after one RTT, it will be 1, then 2, and then after one more RTT, it will be 6. And then you are sending 6, right? You are sending 6. But this 1 is remaining, right? So you will be receiving 3 ACKs. And then this one will be counted in the next cycle. So basically you are receiving 3 ACKs because of the 5 here and the 1 that you have not counted here. You're getting, are you with me? So now it will be 9. Whenever you are sending 9, now you will be receiving 5 ACKs, right? 5 ACKs because 4 ACKs because of the 8 and then because of the 2, right? Because of this one and the 1 that I have not counted here, because of these 2, you will be receiving 1 more ACK. So basically you will be receiving 5 ACK and 9 plus 5 is 14. So the CWND will go something like this: 2, 3, 4, 6, 9, 14, and then it will be actually exponential and it will keep on going something like this. Okay. Okay. So that's how this window will travel. Now, this was the slow start where I just keep on incrementing by 1, or maybe you can say we just keep on doubling. Okay. You can also say in every RTT we are doubling, or maybe in every ACK we are incrementing by 1. Now there is one more algorithm, which is, I mean, both algorithms are basically combined, but there is one more state you can say of the algorithm, in which what we do, we increment by just 1 in 1 RTT. Earlier what we were doing, we were incrementing by 1 in 1 ACK, but now we will be incrementing by 1 in 1 RTT. So how it is happening? In 1 RTT it will be I plus 1, in next RTT it will be I plus 2. If it is initially 4, after 1 RTT it will be 5, after 1 RTT it will be 6. Now can anyone tell me, in 1 ACK how much I'm incrementing? If in 1 RTT I'm incrementing by 1, then in 1 ACK how much I'm incrementing? See, this is your congestion avoidance phase. Congestion avoidance. So in 1 RTT, CWND congestion window is going from CWND plus 1. In 1 RTT, how many ACKs I am receiving? Just a second. Oh no. So suppose what is happening here, in 1 RTT, we are sending, we are basically incrementing by 1. This is going from CWND plus 1. In 1 RTT, how many segments I'm sending? Oh, sorry, how many ACKs I'm receiving? It is equal to the congestion window size, right? Number of ACKs in one RTT is CWND, right? I mean, whatever the congestion window size, I will be receiving that many ACK. So basically, after every CWND, these many ACKs, right? We are incrementing by one, right? So after one ACK, we are incrementing by this, right? After one ACK, we are actually incrementing by this. So that after every CWND, after all of this windows received, I'm incrementing just by one. So now they may also ask this kind of question. So in one ACK, how much you are incrementing in congestion avoidance phase? So we are incrementing just by 1 upon CWND. We are not incrementing even by 1. Okay. Yeah. So now there are actually two variants of TCP. Actually, there could be many variants, but let's just see 2 or 3 variants that we have. One is saying that there are 2 phases, which is slow start and congestion avoidance, and this is also saying that another implementation is also saying 2 phases, which is slow start and congestion avoidance, right? So there are actually 3 implementation. I will talk about the third implementation at the end, which we have not talked about in the theory lectures. That is called TCP Reno, and these are TCP Tahoe implementations. Okay, this is TCP Tahoe implementation, and I think this implementation is not even being used. So anyway, let's just see. So suppose there is no congestion. Okay, things are very, very smooth. There is no congestion. Then what? There is no packet loss. Okay, so suppose there is no packet loss. Things are very, very smooth. Then what will we do? Let's just see. Suppose there is no packet loss. Okay. Then in that case, what you will do? You will start in the slow start phase. Okay, which means you will be keep on doubling your congestion window size. You will keep on doubling to 2, 2, 2 like this, and then there will be a threshold. What is that? Starting threshold, SSTH, right? RSH. Okay, there is a threshold which is called slow start threshold, SHTH RSH, which is threshold, slow start threshold. So basically, there is an initial threshold. You can keep it anything. Okay, it is not necessary to keep it some fixed value. So there is also very, very popular misconception that we think that this threshold should be the half of the window or something. Okay, the threshold we set to the half of the window, that we set after the timeout or something. But the initial threshold, so there are 2 things about the threshold. This is called initial threshold that we are agreeing upon. This initial threshold could be anything. Okay, this could be anything. So maybe it could be anything. And then let's suppose that your congestion window size is 1. And then this is, let's suppose initial threshold is, let's suppose maybe anything, maybe 32. Okay, 32 MSS. Then what you will do? You will be in the slow start till you get your congestion window size to be 32 MSS. Once it is 32 MSS, then you will say that, okay, now let's just move to congestion avoidance phase. This is congestion avoidance phase. Here, you will be incrementing your congestion window just by 1. Here, you will be doubling your congestion window, right? In every RTT. So once you move to this 32 MSS, because that's the threshold, then you will say that, okay, now since this is a 32 MSS, then you can basically just go to the congestion avoidance phase. And currently I'm assuming there is no packet loss or something. Okay, so it's very smooth. Now let's do one question based on this. Let's do one question. Maybe you will get to understand that more. Okay. Just a second. Yeah, let's do this question. So here I'm assuming there is no congestion. If there is no congestion, there is no timeout or anything. Things are very, very smooth. Okay, so let's do this. Consider the effect of slow start on the line with the 10 millisecond round trip time and no congestion is there, which means like things are will be in the slow start till your congestion window is actually equal to the threshold. Once it is equal to the threshold, okay, congestion window is basically should be greater than equal to or less than equal to, greater than equal to threshold, then you will move here immediately, you will move here, right? So once, in this case it is actually equal to, but anyway, like if it is greater than equal to, then you will move here. The receiving window size is, so receiving window size is given to us, which is 24 kb. Maximum segment size is 2 kb. So that's why I'm writing in everything in the MSS. So this is this much MSS. How long does it take before the first full window can be sent? So basically they are saying that you cannot obviously send more than 12 MSS. So how long it will take to get this 12 MSS? And they have not even given the I think the threshold here, right? Since they have not given the threshold, then tell me what will the threshold? So you do not need to even assume some threshold. You do not need to limit yourself, which means initially the congestion window will be 1, then it will be 2, then it will be 4, then it will be 8, and then it cannot be 16 because the 16 will be crossing this, right? So it will be 9, 10, 11, 12. So how much time you are taking till 12? After 8, basically you are going to congestion avoidance phase. See? Okay, sorry. Since there is no, yeah, that's very interesting. Since there is no threshold, from 8 directly you can jump to 12. Yeah, that's very, very nice question. Since the threshold is not given, so from this 8 you can directly move to 12. Why? Because you will always be in the slow start. You are always in the slow start here. You will never need to go to the congestion avoidance phase because the threshold is not given. Okay. Should I take the threshold to be 12 by 6, 12 by 2, which is 6, something like this? Should I make the threshold to 6 because the threshold is not given? No. Basically, there are two thresholds. One is called initial threshold. This is the initial threshold. This initial threshold is either has to be given. If it is not given, then you will not assume that to be anything. Okay. The initial threshold has to be given. If that is not given, then you should not assume it. I'm 100% sure that if this question is given to any of the GATE aspirant, then 99.99%, okay, this is what I'm 100% sure. The 99.99% students will assume the threshold to be 6, which is completely wrong. Basically, in case of no congestion, there is the initial threshold should be given. Okay, if it is not given, then you cannot assume that to be anything. Let me just show you in the book also. See. See here. The TCP starts slow start algorithm and sets initial threshold. This is the actually initial threshold because it starts in the slow start algorithm. So start means it is the initial, right? TCP starts the slow start algorithm and sets the initial threshold or the threshold variable to the pre-agreed value. Okay, it should be the pre-agreed value. It is not something half or something. Okay, but later if the congestion is detected, maybe because of the timeout of the 3 duplicate ACKs, then TCP immediately interrupts the aggressive growth and restart the new slow start algorithm by limiting the threshold to the half of the congestion window. So basically you go to the half of the congestion window only in case of the congestion, not in case of the initial threshold. Is this point clear to everyone? See here, the initial threshold is ... Why it is ... In any diagram it should be ... Why? Because the initial threshold should be some pre-agreed value, and then this threshold, when it is timeout or 3 duplicate ACK, then this threshold is half of the congestion window. Okay, this is the initial threshold, which is actually the pre-agreed value. Is this clear? So here the initial threshold is not given, so let's not take it anything. Okay, and it is actually the standard question. This question I have taken this question from MIT. So if you Google out this question has been taken from the MIT. See, they are saying that after 5 RTT has been sent out, this is, however, it will exceed the, okay. So they have not considered the threshold because it is not given. So you don't limit yourself to, you know, the half of something or something like this. You don't say that, okay, till 6 you will increment and then after that you will not increment. It's not like that. I mean, from 8 you will directly going to 12 because there is no threshold. So you will be, I mean, if you want you can go to 16, but obviously like 16 there is no point in 16 because the receiver window size is 12 just. So that's why you will just say that, okay, whatever is the lesser. So from 8 directly you will go to 12. This is the actual window, right? That is happening. Okay, I hope that is clear to everyone. So this was the case when there is no congestion. Now I think there has been a gate question also. Let's just quickly see that question, right? Okay, I think I currently do not have that question, but yeah, there is a gate question in which also they are saying that there is no congestion and then do these things. So I mean, if there is no congestion, you just be in the slow start, right? Okay. Now let's move to the next case when there is a congestion. Suppose there is a congestion. So there is no congestion, you keep on doubling, and after some point in time, whenever this is greater than the threshold, which is the pre-agreed value, and then you will say that, okay, now you will be just +1, something like this, right? Now, what if there is a congestion? Now there are different ways to implement that congestion. Okay, I mean, if there is a congestion, then one way is to treat this these two congestion, which is timeout and the 3 duplicate ACKs, as same. One way is to treat this timeout and 3 duplicate ACK is different. Okay, so congestion may be because of the timeout or maybe because of the 3 duplicate ACKs. So let me write here. Now there are different implementations that treat those two type of congestion in maybe the same way or other way. This is the first very naive implementation, which is treating the treating those two type of congestion in the same way, which is saying if there is a congestion, then the threshold should be the current congestion window divided by 2. Okay, and the congestion window you are starting with 1. So why it is the case? Let's just see it. Let's take this as implementation 1. So suppose that you are basically dealing with TCP congestion, and initially let's suppose that you are starting with 1, and then your window size is 2, then it is maybe 4, and then maybe 8, and maybe after 8, once you send those 8 packets, then you realize that out of those 8 packets, some packet got lost. Okay, and because some packet got lost, and that's why there's some congestion, and then maybe you experience that only one of the packet got lost, and maybe 3 duplicate ACKs you have received, right? So currently the congestion window size that you have taken is 8. Now suppose at this point in time you felt that out of those 8 that you have just sent, okay, out of the 8 packets, we have just sent, let's suppose one packet is lost, and that is why there is a congestion. Let's suppose you detect that congestion is because of the 3 duplicate ACKs. I mean, you got the duplicate ACKs, okay, at this point in time. Then what you will do, you will say that, okay, let me just start from the initial, which means I will say that, okay, let's be very aggressive, which means I will start my congestion window again from 1. Okay, and then 1, 2 like this. And now this time, can I go to 8? Tell me, is it a good idea to go to 8 this time? Since 8 was very too much for me. I mean, for the network it was too much, right? So now if I'm starting again, is it a good idea to go to 8? So here I just experience a congestion and I want to start again, right? So let me write in this way. Yes, if I directly go to 8, then there will be a congestion, right? So suppose there's a timeout, or maybe through anything. Okay, currently I'm actually not differentiating it, but let's suppose this is 3 duplicate ACKs. Then you will say that, okay, out of this 8, maybe some packet got lost, and let me start from 1. So if I again do the same thing, 1, 2, 4, 8, then since 8 is too much for my network, then again there will be 3 duplicate ACK timeout, something like this, right? So it's not a good idea to go to 8 at this point in time. I will go to 8, but I need to figure out that what is the best thing that I should be doing. Maybe 8 is not the best. Maybe 7 is best, right? Maybe 6 is best. So I will go to 4. That's not a problem. But after 4, I might want to go to linearly. I want to approach it, but linearly. Something like this. Doesn't it seem a good idea? If 8 is too much for my network, maybe because of 3 duplicate ACK or something like this, that we will see. But if 8 is too much for my network, I will start from 1 again. Maybe I can start from 4. Maybe okay. I mean, it is also a good idea, but let's suppose I'm starting from 1. By the way, what do you think? Should I be starting from 4 or should I be starting from 1? You're getting my point? Are you with me? So basically what I'm saying, let's suppose at 8, there is some congestion in the network. Now, maybe I can start with the 4, because anyway I'm going to the 4 again, right? I mean, it depends on my implementation. Okay, maybe I can start directly with the 4, maybe I can start with the 1. Let's suppose 4 now, I'm just starting with the 1. Every time there is a congestion I detect, I get too much or afraid, and I just start with the 1. Okay, every time I get congestion, I get afraid, and I'm starting with the 1, and then at 1, 2, 4. But obviously it is very clear it is not a good idea to directly go to 8, because 8 is too much for my network. So I will approach it after 4, maybe linearly. Maybe after 7, I might get a congestion here again. Then maybe I will just stop at 7, right? Something like this. And if 8, if I'm getting a congestion, then maybe I again need to start with the 1 or something, right? So anyway, it is not a good idea to go to 8 directly. I mean, from 4 to 8 directly. So that's why I'm just incrementing linearly. So this is called, whenever there is a congestion, okay, maybe through duplicate ACKs or timeout, whenever there is a congestion, I was in the slow start phase. Whenever there is a congestion in the slow start, currently the congestion is in the slow start, so it is a slow start. Why it is slow start? Because I'm starting with 1, but it is exponential increase actually. Okay, so whenever I'm in the slow start, okay, if there is a congestion, then I will again start from 1, which means I will again go to the slow start. If there's a congestion which is through duplicate ACKs or timeout, then I will again go to the slow start, and then this time I will do one thing. I will say that once the 4 is reached, I will go linearly, which means I will go to the congestion avoidance phase. Once the 4 is reached means, what is this 4? It is the threshold that I can have, which is congestion window by 2, which means once this after this was 8, I don't want to get to 8. I will just limit myself at 4, right? I mean, now this time I will just stop at 4. I will not go to 8, which means I will say that, okay, till 4 I will go, and then after 4 I will go linearly. So see here, that's what it is happening. So whenever there is a congestion, I will say that, okay, if there is a congestion in the slow start, then I will keep to the slow start, and then slow start means the congestion window is 1. Slow start always means the congestion window is 1, and the threshold will be this, right? Threshold will be this, and I will be in this. Now, obviously, like after 4, I will go here. Now, suppose in the congestion avoidance also, I get the congestion. Okay, I'm in this phase, I'm going linearly. Let's suppose at 6, I get the congestion. If I'm getting the congestion here, then again, I always get too much of afraid. I get the slow start, which means I will starting from 1. And then the threshold, I will be keeping it to the half always. Let me give you some example. Okay. So what is happening here? Initially, let's suppose your initial threshold is suppose 16. Okay. And now let's do the complete story. I'm starting from 1, then 2, maybe 4, then 8. I can go to 16 ideally if there is no congestion. Okay. Let's suppose if there is no congestion. First case is that no congestion. Okay. Then ideally after 8, I can go to 16. And then since it is a threshold for me, then I will go to 17, 18, 19, like that, right? Like that, I will be keep on going. I hope that is fine to everyone. Now, suppose there is a congestion. Okay. I mean, there could be a congestion anywhere. If initial threshold is 16, let's suppose, unfortunately, I got some congestion here. Okay. Some packet loss. Then what will I do? I will always start from the slow start. And then this time I will not reach to 8. I will keep myself to just 4. 1 to 4. After 4, I will linearly go. Okay. I will linearly go to 4 to 5 to 6 to 7, like that. 8, I will keep on going. Right. If I'm getting something. But let's suppose after the 7, or maybe after the 6, I again get the packet loss. Whenever I'm getting the packet loss, I'm always saying that, okay, start from 1. Now my congestion window size will be just 3, which means from 1 to 2 I will go, but from 2 to 4 I cannot go. So from 2 I will just go to 3, right? I will just go to 3. Why I'm going to 3? Why I'm going to 3 here? Because now let me just write the thresholds. So here the threshold after this, the threshold is just 4. Okay. And then once the packet is lost, the threshold is just half. The threshold is 3, right? So I can go till the threshold. And now this, I'm still in the slow start phase. I'm still in the slow start. Okay. This 2 to 3 doesn't mean that I'm incrementing linearly. I wanted to increment exponentially. I wanted to write 4 here, but because of the threshold, I'm just writing the 3. Now I will go linearly 4, 5, like something like this. So basically, whenever there is a packet loss, at that time I keep my threshold immediately half to the current congestion window, which is 8 to 4 and something like this, and I will always start from 1. That's what it is saying. Okay, this implementation is quite easy, which says whenever there is a okay, let me open here. Whenever there is a packet loss or there is a congestion, then you immediately go to the slow start. Always go to the slow start. See, whenever there is congestion, go to the slow start. Congestion, go to the slow start. That's all, right? Now there is another implementation which actually differentiate both type of congestion. Okay, but before that, maybe we can solve this. TCP start with the data transfer and set the threshold variable to the ambitious value 16 MSS. Okay, see, that is given to us. The initial threshold is given to us, and then they're saying TCP begins the slow start with the CWNDH1. Timeout occurs after third RTT. So after 1 RTT, 2 RTT, and third RTT, right? There is a timeout after 8. Then if there is a timeout, then what you will do? Then go to the slow start again. Okay, so I mean you will go to the slow start. If this is given to be 16 MSS, so maybe you can go till the 16. So maybe let's suppose if after 12 there is a 3 duplicate AC case, then you will be again starting from 1. So whenever there is a packet loss, maybe timeout, 3 duplicate AC case, you will always start from 1. Okay. So see here. See, whenever there's a packet loss, timeout, or 3 duplicate AC keys, that you always drop down. You always start from 1. Then till the threshold, you keep on. This is exponential. After it, it is very linear. Suppose there is some problem, you again drop down. Then it is exponential till the threshold. Then it is linear, right? This is what it is happening. Now there is another implementation which differentiate in 2 type of congestions. Actually, it is saying if congestion is because of the 3 AC case or timeout. It is saying if it is because of 3 AC case, then the congestion might not be that much severe, right? Then I will not start from the 1. If this is 3 AC case, then the congestion is not that much severe. Then I will say that, okay, I need to slow down. That is okay, but not from 1. I will say that, okay, I will slow down from the half, which means, let me tell you what do I mean by that. So see, here what I'm doing, let's suppose after this, there is a congestion. After 8, there was a congestion. So I did what? I started from 1, right? I started from 1. But this implementation is saying, just let me know congestion is because of what? Okay. Let's suppose the congestion is because of the 3 duplicate ACKs. It is saying, let's suppose the congestion is because of the 3 duplicate ACKs. Then it says that do not start from the 1. It says, let's just start from, if it is because of 3 duplicate ACKs, maybe we can start from the half of the congestion window, right? Maybe we can start directly from 4. So let's not do from this. We can directly start from 4 and then 4, 5, 6, 8, something like this, right? So we will say, if the congestion is because of 3 duplicate ACKs, then I will be starting from half of the window. I mean, I will be starting from 4 and then I will be in the congestion avoidance phase. So I will not be reaching till 4. There is no point in reaching till 4. That's what it is saying, which means it completely eliminates the idea of the slow start in case of 3 duplicate ACKs. And if that is because of the same thing is because of the timeout, let's suppose the same thing is because of the timeout, then you will start from 1, right? Yes, same as previous. So you will basically reach till this 4. You will say 1, 2, and then 4. You will reach till this 4. Now you are directly starting with the 4, but here you will say that, okay, if it is because of timeout, then the congestion window will be just 1, and then threshold, okay, threshold will be half of this congestion window that you had. So basically, generally we write the threshold upper so that yeah, so that it is easy to write. So basically, we will say the congestion window by half, which means after 4, like I will be going linearly. But now here I say the congestion window itself, the current congestion window by 2, and the threshold is actually like here that threshold is not meaningful. I mean, meaningful in the sense threshold is basically meaningful in case of only slow start, because it is slow start threshold, right? I mean, threshold is not meaningful here. So, I mean, you can write anything. So generally we just write it congestion. Anyway, the threshold is not meaningful in case of congestion avoidance phase, right? Because in congestion avoidance, there is no threshold. You do not have any threshold or some limit. You're just incrementing linearly. Okay. So in case of congestion avoidance, the threshold is not much useful because it's a slow start threshold. Okay. So you can keep it anything. Now let's just take some example. Suppose, let's suppose the initial threshold is given to you. Which is suppose 8, or maybe let's suppose 16. And then they're saying start from 1, and let's just see that what is happening. 1, 2, and let's suppose after this 4, and maybe after this 8. And if there is no congestion, maybe you will go to 16, then 17, like that, right? You will keep on incrementing. And till what point you can increment? Till what point you can increment? Till it becomes the equal to the receiver window size. Yes, very good. It becomes the equal to the, let's suppose this is the actual window, till it becomes equal to the receiver window size. Okay. So suppose after this 4 only, you are getting some congestion. Maybe it is because of the timeout. Since it is a severe congestion, you will say, okay, let me start from 1. What will the threshold? Will be just 2, right? So you will start from 1, you go to 2, and then after 2, you will not go to 4 directly. You will go to 3, you will go to 4, 5, like this, right? 6, 7, like this. Suppose that after 8, there is again a congestion, and now this congestion is because of 3 duplicate ACKs. Okay. So in this case, you will say that since it is a congestion because of 3 duplicate ACKs, that's why congestion is not that much severe. Now my congestion window size will be, I will not cut down to half, sorry, cut down to 1. I will just cut down to half, which is 4. Here the threshold does not matter much. I mean, the threshold is not very significant, so let's not worry about it. Okay. I mean, you can write the threshold equal to congestion window or something, but it's not too much significant to us. Okay. So this is 4, 5, 6, 7 like this. Let's suppose 8, 9, 10, 11, 12. And then suppose now there's again a congestion, because again, let's suppose there's a 3 duplicate AC cage. Then what you will do? You will say now the congestion window will be 6. You will be starting from 6, but you will not start from 1. That's the only difference. You will start from 6, 6, 7, 8, 9, something like this, 8, 10. Now, suppose there is a timeout, then you will start from 1. Now, obviously, since you are in the slow start phase, now the threshold will matter here. What is the threshold? It will be the half of this, which is 5. Right? Okay. So this is 10. So basically, you start from 1, then 2, then 4. And after 4, you should be writing 8, but this is the limit. So that's why this is 5. Okay. Now this is a slow start, and you immediately move to what we call a congestion avoidance phase, right? Is this clear to everyone? How we are treating? Okay. So only the way we are treating two different kind of congestion is the only difference in these two implementations, right? So one is the 3 duplicate AC gauge, another one is the timeout. Now, in the question, it must be clear that which kind of implementation we are using actually, right? So let's see the gate questions and let's just check if they make it clear or not. Okay. Okay, the questions I think that has been deleted because just a second. Okay, so let's see some questions. What they are saying is that consider an instance of TCP additive increase multiple decrease algorithm. So this algorithm is called additive increase multiple decrease. Okay, which means you are incrementing additively, but whenever there is a loss or something, you immediately either cut down to half or cut down to 1. Your CWND is either 1 or CWND is either immediately you cut down. Multiple decrease means you immediately do some measurative actions. Okay. So now let's just see that what they are saying. Now, where the window size at the start of the solo start is 2 MSS. So they are starting with the 2 MSS. And the threshold at the start of the first transmission. Yeah, see, that's very interesting, right? So at the start of the first transmission, threshold is given. That's called the initial threshold. They will always give the initial threshold. Okay. Don't make any assumption about the initial threshold. Let me write initial threshold, which is given to us is 8 MSS. Assume that a timeout occurs during the 5th transmission. Find the congestion window at the end of the 10th transmission. Okay. After during the 5th transmission, there is a timeout. Okay. So initially it is 2, then it will be 4, then it will be 8, and then it will be 9. So it is the first transmission, second transmission, third transmission, fourth transmission, and then 5th transmission, right? In this 5th transmission, during this, whenever you are sending the 10 packets, then maybe one of the packets has got lost. And then they are saying, assuming the timeout occurs. So now you are assuming the timeout is occurring. What is find the congestion window size at the end of the 10th transmission? So since there is a timeout, what you will do? Congestion window should be 1 or something. See, interestingly, they have, okay, that's 2 or something, that's okay. But interestingly, you notice one thing. The question is not about the 3 duplicate AC case. Because if this is about the through duplicate ACK, then we will be asking a question, which implementation you are using, right? Since it is about the timeout, no, they have not given any implementation. So since it is about timeout, so that's why like any of the implementation will work, right? So there will not be ambiguity about the implementation. Since it is about the timeout, that's why you can say that okay, any of the implementation will work here. So now it will be starting from 1. So this is 1 transmission, 2nd transmission, 3rd, 4th, 5th, 6th transmission, then 2. Then what will the threshold? Is 5, right? 1, 2, 4, and then immediately 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9 transmission, and then after 5 it will be 6. Sorry, you will be starting from 2. Sorry about it. Yeah, you will be starting from 2, and then after it 4, then 5. So it is first transmission, 2nd, 3rd, 4th, 5th, 6th, 7, 8, 9 transmission, and the 10th transmission is 7 MSS, right? So they are saying find the congestion window size at the end of the 10th transmission. So it is 7 or it is 8. End of the 10th transmission. What do they mean by the end? Yeah, I think it should be 7. When you are transmitting after 1 RTT only, it will be 8, right? After this transmission and after the 1 RTT, it will be 8, but currently it is 7. So I think answer should be C, right? Okay, there is ambiguity. Window size will be 1 MSS, 2 MSS given the question. This due to. Okay, this was marks to all because the confusion was here that it should be 1 or 2 MSS. I mean, if like they have not made it clear that after timeout also the congestion window size should be 1 MSS or 2 MSS, something like this, right? Okay. So anyway, I hope you understood this question. Now, there the interesting one that I want you to notice is that this is implementation dependent because they are asking about the timeout, right? If they ask about 3 duplicate ACK, then it will be the implementation dependent. Why not 8? It is not 8 because this is they are asking at the end of the 10th transmission. So the moment you finish the 10th transmission, after the 1 RTT, see 8 is see you send the last packet, right? You send the last packet. So let's suppose these are the 7 packets that you're sending. 7 packets you're sending 1, 2, 3, 4, 5, 6, 7, and then you count the RTT from the last because you say that once this ACK is received, and then after this, after this 1 RTT, you will be incrementing it to 8. But at the end of the 7 transmissions, it is just 7 only, right? Once you receive the ACK for this last one that you have just sent, then it will be 8. Okay. End of the 10th transmission. 2, 4, 5, 6. 1 second. 2, 4, 8, 9, 10. 2, 4, 8, 9, 10. Then 2, 4, 5, 6, 7, right? 2, 4, 8, 9, 10. Okay, they are starting with 1. Anyway, like again, this is marks to all because either you start with 1 or 2. This is debatable. Okay, so let me move further. Now let's do this question. Again, as you notice in this question also, they are saying timeout, right? I mean, they are not saying 3 duplicate ACKs. Let's just see this question. The size of the congestion window size is this. According to our, no, why it is correct? We are starting with 2, 4, 5, 6, 7, right? Okay, they took 6 plus 1. At the end of transmission. No, I actually think this should be 7 only. Reason being is that at the end of the 7th transmission, you do not increment that to 8. You increment that to 8 after 1 RTT, not at the just end, at the end. I mean, you send 7 packets, right? 1, 2, 3, 4, 5, 6, 7. And the moment you receive the ACK for this, that you just sent at the last, then you will make it to 8. You will not make it to 8 before it. That's my reasoning. I hope that is correct. I will check the answer, who has written this answer. I will verify that answer later. But according to me, it should be 7 only. And the reason is obvious, that at the end of 7th, you are not immediately incrementing. You receive the ACK, then only you increment, right? At the end of 10th, you are not immediately incrementing. That's the point. So let the size of the congestion window here, TCP is 32 kb. MSS is 2 kb. So congestion window size is 16 MSS. The round trip time is 100 milliseconds. And the maximum, the time taken in the millisecond by the TCP connection to get back to the 32 kb congestion window is, the round trip time is this. Let the size of the congestion window is this, when the timeout is there. So there might be some sequence of events, and then the moment this is 16, after it there is a timeout. That's why I need to start with 1. What will the threshold? It will be 8, right? Then 1, then 2, then 4, then 8, and after 8 I will take, it will be 9, 10, 11, 12, 13, 14, 15, 16. So how many RTTs I have taken? There is from 1 to 2, there is just 1 RTT, right? So you can count RTT like this. There is 1 RTT, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 RTTs I have taken, right? So that's why 1100 milliseconds. Interestingly, as you can notice, this is a timeout again. This is not the 3 duplicate ACKs, because in case of 3 duplicate ACKs, they have to tell that which kind of TCP they are using. You understood it? In case of timeout, there is no confusion. That's why they can give this question. Okay. Now let's solve this question. Yeah, this is good question. Good in the sense like this is the almost same question that we did here as a MIT question. Do you remember that MIT question? So here they have not, they said like there is no congestion, right? Since there is no congestion, so I will always be in the slow start phase. So let's just do this question in a similar way, because I think there is no congestion here. This question has been asked recently. This is same question that we did as an MIT question, but let's just do it. Consider a TCP connection between a client and server with the following specification. Round trip time is 6 milliseconds and size of the receiving advertised window is this, slow start threshold. Anyway, like I think maybe you can try this question as an homework, because it will be a good practice to you. Okay, just try it as an homework and then we will do it tomorrow. I will upload the slides today. Okay, so try it as an homework. Yeah, so I think we are almost finished at the TCP. Just try all the TCP questions, and whenever you are dealing with this congestion control kind of questions, you will notice one thing: there is a timeout. Okay, if there is a 3 duplicate ACKs, then there will be ambiguity, because which kind of implementation we are using. So that's why they generally ask with the timeout only. Okay, cool. So I hope that is fine. Okay, so let's meet tomorrow. Thank you, everyone. Take care. Bye bye.